Well, you're made of water, and water's effectively lots of protons, and I think of protons like little sticks that spin around. They have a thing called spin. Right now, your protons are all pointing in different directions because they can go wherever they like. But when we put you inside this big magnet, they all lie down flat with the magnetic field. That's how they like to be. But remember, they're still all spinning. So here are the protons spinning in the magnetic field, and they're inside this big magnet, and then we hit them with the second magnetic field that pushes them out of alignment. When you're in an MRI scanner, you hear this bang, 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 bang noise, and every time it goes bang, that's the protons being knocked out of the way. They'd like to get back to where they were, to the laziest position, and so they spin back into alignment. As they spin back, they lose energy, and that energy is in the form of radio waves, and we pick up the radio waves using a detector. So essentially what we're doing in there is we're kicking your protons out of alignment. As they spin back, they give off radio waves, and we detect the radio waves they give off. And the secret of the MRI is that they give off different types of radio waves, different frequency of radio waves, depending on the local magnetic field that they're in. So they're all in this very strong magnetic field, but some of them, because of where they are in the body, find themselves slightly shielded or slightly exposed to that magnetic field, and the spin goes back slightly faster or slightly slower, and that we can pick that up with the receivers. So we're measuring the frequency of those waves as the protons come back into alignment. And so the things that affect how fast they spin back are things like the presence of fat, water, bone, air, all these things that we'd like to be able to see in the body. So by doing some clever maths, we can work out when groups of protons spin back and they give off the radio waves, we can work out whether they were near these different types of tissue. Then the computers go to work and they build up a picture of the whole brain. So what I just described will give you the presence of things like fat and bone, and those all make the little local magnetic field slightly different. So those will give you an anatomy scan, a picture of your head, a bit like a fancy X-ray. But there's one molecule that's really good at screening things from magnetic fields, and it's hemoglobin. So hemoglobin contains iron. Iron's a ferromagnetic material, and so protons that find themselves in the shadow of hemoglobin, near hemoglobin, have a very different spin frequency when they come back. Hemoglobin is carried in blood, and the spin frequency changes, in fact, depending on whether the hemoglobin has oxygen bound to it or not. So by doing even more clever mathematics, we can work out whether these protons are near oxygenated or deoxygenated blood. Now it's easy. So you give someone a job to do, like a visual task. Maybe they're going to look at something, or maybe they're going to count to 10, and some parts of their brain become activated. When parts of the brain become activated, the brain cleverly supplies them with more oxygen so they can work properly. That oxygen will be coming in on the hemoglobin, and it'll change the frequency of the responses we see from the brain. And so we can see where in the brain oxygenated and deoxygenated blood is flowing. In the olden days, you'd do that by making something in the blood radioactive and having a Geiger counter detect where it was. That's called PET scanning. This technique doesn't require any radioactivity. It just measures the presence or absence of this oxygenated blood through its effect on the proton spins. People fight about this a bit. Effectively, we think the resolution on a scanner like this, on a sort of a normal research scanner, is a couple of millimeters, so maybe just under 2 millimeters. The next generation of scanners that are now in use, the 7 Tesla scanners, which have about twice the magnetic field of this one, they claim that they can see things smaller than a millimeter, maybe even down to 500 microns. And there are groups one group in Europe and one group in America who have very high field scanners and who scan for a long time, who think they can get down to hundreds of microns. So we're still not at the level of a neuron, but we're at the level maybe of a neuronal map, a ocular dominance map, or some sort of local circuits. Yeah. So a single experiment tends to go in a burst of about 5 minutes. We're all about patient comfort or subject comfort, and so we like to give people enough time to have a breather between scans. So typically what happens is you'd be recruited from an experiment, you'll go in for an hour, and that hour would consist of maybe 7 or 8 experiments, functional scans, and then you'd come out again. So we'd get the whole thing, maybe your whole brain anatomy and some functional data in about an hour. It's a fact that your visual cortex contains lots of little maps of visual space. And this was worked out very painfully and slowly over the early 20th century by people looking at damaged brains and people looking at animal models with electrodes. It took them decades. And when functional brain imaging came along, it was possible to do a thing where you would map out the whole of visual space in about 5 minutes and look at the effects on visual cortex. And when you do that and do some fancy visualization, you can see all the maps in visual cortex just presented all at once. So 100 years worth of work in about 5 minutes, and it just looks beautiful. And I just keep thinking those physiologists from 1920 would have given their eye teeth to see those maps that we're just looking at.